In this video, we are going to discuss the idea of entropy and find the change in entropy for several processes. To begin with, let's just define entropy. Entropy is the Boltzmann constant multiplied by the natural log of the multiplicity of a system. The multiplicity of the system is an enormously large number, but the natural log of that enormously large number is just a large number. And if we take a large number and multiply it by something, say 10 to the negative 23, like the Boltzmann constant, we end up with an entropy that is fairly small. So, one of the nice things about entropy versus multiplicity is that entropy is a fairly small number for most systems, while the multiplicity is an extremely large number. In a sense, the more fundamental quantity is the multiplicity, the number of microstates available to a system. But because that number is so large, it becomes unwieldy to work with. And as we'll see later on, entropy actually has some nice connections with temperature and pressure and other variables of a system that we would really like to talk about. So, to begin with, let's just do an example where we find the entropy of a large Einstein solid. So, for an Einstein solid, the multiplicity is given by EQ over n raised to the n. This is derived in Chapter 2 of Schroeder. And this multiplicity requires that the number of units of energy Q is much, much larger than the number of units of the number of Einstein solids, the number of oscillators in the Einstein solid n. And in this case, 10 to the 24 is much larger than 10 to the 22. So we are okay. Taking the natural log of this multiplicity, we find that we get n times k. The n out front comes from the exponent of our multiplicity function, because we remember that if we take the natural log of something that has an exponent, we can pull the exponent out front of the log as a multiplying factor. And then taking the log of EQ over n, the plus 1 comes from the natural log of E, which is, of course, 1. Plugging our values for n and q and the Boltzmann constant into this equation, we find that the entropy of this system is 0.77 joules per Kelvin. The Boltzmann constant gives us the units of entropy as joules per Kelvin, and we will find later that these units are actually quite useful in relating our entropy to other things that we might care about, such as temperature. Some nice properties about the entropy. First, the multiplicity of two systems that are combined is the product of those two multiplicities. So the multiplicity for a combined system A and B is the multiplicity of A multiplied by the multiplicity of B. However, if we take the entropy, we can use the property that the log of a product of two any numbers, the log of the product of two numbers is equal to the sum of the logs of those numbers individually. So we end up with the entropy of two systems adding. So instead of having to multiply two very, very large numbers, we get to add two relatively small numbers, which makes mathematics, again, much nicer for us with the entropy versus the multiplicity. The second law of thermodynamics says that any large system in equilibrium will be found in the macro state with the greatest entropy. You could also replace entropy here with the macro state with the greatest number of available microstates, or multiplicity. And this is just a statement of statistics. In any very large system, there will be many, many more microstates available to the system near its equilibrium position or equilibrium temperature than at any other macro state, right? So for example, if I put a really hot pan next to a really cold pan, the hot pan will give energy to the cold pan until they're at the same temperature. Why? Because there are many, many more ways to have the hot pan give energy to the cold pan than vice versa, or for the hot pan to just hold on to all of its energy. If the energy is allowed to move, it will move in such a way that the number of microstates available to it increases, and that moves the system towards the greatest possible entropy. We can also restate the law of thermodynamics as entropy tends to increase. Whenever there is an interaction, that interaction will tend to increase the entropy of the universe. For example, a hot pan giving energy to a cold pan increases the number of available microstates because there's more ways of rearranging the energy between two of the pans rather than if one pan has all of the energy. And that tends to increase the entropy. All right. Another thing to think about is Maxwell's demon. So back in the 1800s, a guy named James Clerk Maxwell decided to think about a thought experiment of what if I created some kind of a demon, some kind of a mechanical device, or there was an entity or someone smarter than people who could separate fast-moving particles from slow-moving particles. So imagine that you have a box and you have a gate in the box. And the box is initially filled with air at thermal equilibrium. So everywhere in the box you have air that is at some temperature. And then you install a gate in the middle of the box. And the gate allows fast-moving particles to go, say, to the right through the gate and allows slow-moving particles to go to the left, but it doesn't allow vice versa. So slow-moving particles can never move to the right through the gate, and fast-moving particles can never move to the left through the gate. And the idea here is that eventually all of the fast-moving particles would end up on the right side because fast-moving particles can move to the right through the gate only, and all of the slow-moving particles would end up on the left side. And in an air, like in any kind of a normal gas, there's a distribution of speeds. So not all of the molecules in say, air at room temperature are moving at the same speed. They're moving at many, many different speeds. So it would be possible to separate out the particles that are moving faster from the ones that are moving slower. If you were able to do this, you would end up with a hot gas on the right side where all the fast-moving particles are, and you would end up with a low temperature gas on the left side where all the slow moving particles are that don't have as much energy. And the idea is that if you could figure out a way to do this, you could decrease the entropy of this system by basically taking it out of thermal equilibrium. And hypothetically, you could do this with very little work or energy done. You just have to come up with a really clever gate to separate out the particles, and you would suddenly be decreasing the entropy of the universe. And many people have tried to do this and come up with various ideas, but there are no ideas for a device that could do this that would actually decrease the entropy of the universe overall. So even if you were able to create a gate that functioned in this way, that allowed fast particles to move to the right and slow particles to move to the left, and you could separate out the particles based on their speeds, the energy that you would have to supply in order to make the gate function that way would generate at least as much entropy as you removed from this box system by organizing it into hot and cold regions. And so the idea is, even if you could create something like this that would decrease the entropy locally of this system, you would still end up creating enough entropy somewhere else in order to make enough energy to power the gate, right? Whether you're burning oil, for example. When you burn oil, that is an entropy producing process. So you could burn oil to run your gate, and you would generate a ton of entropy by burning the oil, and you could then reduce the entropy of this system locally, but you would never break the second law of thermodynamics because you'd be creating a lot of entropy somewhere else. So to this day, people there are no good ideas for a Maxwell's demon that would actually reduce the entropy of the universe as a whole. And it is considered to be not a possible thing to do. Okay, now let's look at a specific entropy for an ideal gas. We will begin with an indistinguishable ideal gas that has a multiplicity that is given by the equation at the top left here. The multiplicity depends on the volume, the number of particles, the energy, and the mass of the particles. And this equation is derived in chapter 2 of Schroeder. If we take the natural log of this, multiply it by k, and use the Stirling approximation, we end up with the equation at the top right. This is known as the Sackur-Tetrode equation, and it is the equation for the entropy of a monatomic ideal gas. The monatomic means that there are 3 degrees of freedom for this equation. Okay, but this is for indistinguishable particles. If we had distinguishable particles, then our multiplicity equation changes somewhat. Specifically, it loses a factor of 1 over n factorial in the denominator. The 1 over n factorial in the indistinguishable particle case is to take into account the fact that we could rearrange all of the particles at any given state without being able to tell the difference, right? So if a particle is in the top left of the room, so for example, if we're talking about like a room full of gas, I could switch the particle in the top left of the room with a particle in the bottom right. And because those particles are indistinguishable, I wouldn't actually be able to tell the difference when I swapped them. That's what this 1 over n factorial term in the multiplicity gives us. If we assume all of the particles are distinguishable, then we could tell if we switched any 2 particles in our gas, and we lose that factor of n factorial. Now, an interesting problem with distinguishable particles is that, as you will see from the worksheet, if you do something very simple, like remove a partition between 2 identical gases, it looks like you can decrease the entropy of those gases just by, say, removing the partition between 2 sets of identical gases. And of course, this shouldn't be the case, right? I shouldn't be able to remove a partition and drop the entropy of a system. It seems to violate the second law of thermodynamics. And it turns out that this is actually a really good argument for the fact that fundamental particles are indistinguishable. Because if they are distinguishable, it seems like we can violate the second law of thermodynamics. And if they aren't distinguishable, then we can't. So this is one of the ideas in physics that leads us to believe that fundamental particles, electrons, protons, atoms, for example, are indistinguishable. We cannot tell the difference between them. All right, now let's look at a few specific examples of a process and see if we can figure out how the entropy changes throughout that process. We will begin by looking at the isothermal expansion of a gas. This gas will be expanded in a quasi-static way, so it'll be expanded very slowly such that our system variables like temperature and pressure are defined well throughout the process. We will leave the gas in thermal equilibrium at all times, and the system is in contact with a large reservoir that does not change temperature. So the idea is, as the gas expands, the reservoir can give heat to the gas in order to maintain a constant temperature for the reservoir. Okay, so let's think about the work done on the system. So the first question is the work done on the system during this isothermal expansion positive, negative, or 0? And the answer to this question is that the work done on the gas is negative. The force of the piston on the gas is to the left, and the piston is moving to the right, which means that the force is moving in the opposite direction of the displacement. That is negative work when your force is in the opposite direction of the displacement. So negative work is done on the gas. Question 2 is, after isothermal expansion, the internal energy of the gas is increased, decreased, or unchanged. if we remember the equipartition theorem, which says that the energy of a gas is just equal to 3/2 nkt. For, say, an ideal monatomic ideal gas, it's 3/2 nkt. That means that the energy of the gas is directly proportional to the temperature of the gas. For an isothermal expansion, temperature is constant, which means that energy must be constant. So therefore, the energy of our gas remains unchanged when we undergo an isothermal expansion. Next, we will think about the change in entropy for an isothermal expansion. So the question is, how does the entropy change when we do an isothermal expansion? Does it increase, decrease, or remain unchanged? To think about this, we need to go back to our expression for the entropy of an ideal gas. Okay, so what we're going to do is we're just going to write down our initial entropy, our final entropy, and then find the difference between them and see if that's positive, negative, or zero. The initial entropy we can write as our entropy equation where we've replaced V with V initial. Because the energy doesn't change, U is constant. We're not changing the number of particles, so N is constant. So all of the other variables in our equation are just constant. The same thing is true for the final entropy. Everything is constant except for V final. And when we subtract these two equations from one another, we get NK times the natural log of V final minus V initial. All of the other terms inside of the natural log just subtract away when we take the difference between these two. Because remember, the natural log of a product is equal to the sum of the two natural logs. So we can pull the natural log of V initial out into its own term. And therefore write, say, for example, the natural log of V initial plus the natural log of all of the other terms inside of the natural log in our entropy equation. And when we subtract the initial from the final, those constant terms just cancel out. So we end up with a positive change in entropy because our final volume is larger than our initial volume. So we're taking the natural log of a number greater than 1, which is always positive. So we have a positive change in entropy for our isothermally expanding gas. Next, let's think about an isobaric change or an isobaric expansion. In this case, we are keeping the pressure constant. We're still using a quasi-static expansion, so it's happening slowly, and our system is staying in thermal equilibrium throughout the entire process. And we keep the system at constant pressure. All right, so the work done on the gas during an isobaric expansion is again negative. Again, the force is pointing to the left, the piston displacement is to the right. That is a negative external force acting on our gas. The internal energy of the gas is slightly more interesting. As the gas expands, we need to keep the pressure constant. But if we think about, for example, our ideal gas equation, PV equals NKT, this is solving for pressure. Pressure is NKT divided by volume. If we want to keep the pressure constant, as the temperature increases, or as the volume increases, the temperature must increase as well. That is the only way to keep pressure constant in the ideal gas equation. And so if we're increasing the volume and keeping the pressure the same, we must increase the internal energy of the gas. So the answer to this question is increase the internal energy, which is deeply related to the temperature of the gas, increases as we expand at constant pressure. Finally, we'd like to ask, if the isobaric expansion happens, how does the entropy of the gas change? Does it increase, decrease, or remain unchanged? To think about this one, what we're going to do is we are going to, again, go back to our entropy equation, But now we have to be a little more careful because volume is not the only thing in this equation that is changing. Notice that as the volume increases, the energy of the gas also increases. So V changes and U changes. What we would like to do is we'd like to write this explicitly in terms of the thing that we know is changing, the volume, and constants. And the thing that we know is constant is pressure, not energy. So what we'd like to do is we'd like to replace our energy with a expression involving pressure and volume. And we can do that by invoking the equipartition theorem and the ideal gas law. So the equipartition theorem says that the energy is equal to 3/2 nkt, and the ideal gas law says that nkt equals PV. So we can simply write the energy as 3/2 PV. Where I have put a subscript I on the volume in our second term here, the second line, but not on the pressure because the pressure doesn't change. Then we can just combine the volume terms to have volume to the 5/2 inside of our natural log, and everything else inside of the natural log is a constant. We can do exactly the same thing for our final entropy, and when we subtract them off, we get that the change in entropy is 5/2 NK ln V final over V initial. The 5/2, remember, if you take the natural log of something with an exponent, you can pull that exponent out front and make it a coefficient on the front of your natural log term. So the exponent 5/2 turns into the coefficient out front 5/2. Since our volume increased, our entropy also increased. In this case, our entropy actually increased more than it would have in an isothermal expansion, because we are not only increasing the volume, but we are also increasing the temperature along with the volume as we expand the gas.